include a omnidirectional drive system with 3 wheels that allows the robot to translate across the field at any angle without changing its heading at speeds over 0.5 meters per second. Motor power and control is from 3 small motor drivers that have been integrated into a PCB that fit directly onto the Raspberry Pi. The subframe is designed with a modular approach that allows easy customization of parts. An example of this is the travel height of the robot, which simply requires new 3D printed mounting blocks.
Of the alternatives, a solenoid was chosen for the kicker as it met the most criteria compared to pneumatic and spring-loaded systems. The kicker and dribbler was controlled by the AI system, with control pins for dribble, charge and shoot. The kicker's charge circuit would step up the battery voltage to 60 volts, with a 555 timer used at 9.3 kHz to achieve this. The maximum kick speed generated was 1.4 meters per second, which was short of the required 2.5. Otherwise, the kicker works seamlessly. The dribbler was robust and provided excellent ball control, using rubber and a tacky surface known as tapered drum. Overall, the system integrated extremely well and performed as required.
The computer vision module's role is to accurately identify objects of interest based on their colour and communicate the object's distance and bearing to the AI navigation module. The module takes raw frames from the Raspberry Pi camera in the RGB colour space. The colour space is normalised to eliminate noise and shadows by dividing each channel's value by the sum of the 3 values combined at each pixel. Objects of interest are identified by thresholding their particular colour and calculating the contours of the resultant binary mask. Using the pixel dimensions of a contour, an object's distance and bearing can be calculated using the object's known size and the camera's particular focal length. For objects within 200 millimeters, the distance is calculated with only a 0.5% margin of error.
Which has the job of taking and sending information to and from other subsystems. Given information about its surrounding environment, the AI is designed to make informed decisions on what actions to take, capable of performing searching, retrieving, dribbling, and shooting actions. The AI module is designed with a reactionary response in mind, preferring quicker, in-the-moment decisions to slower map processing and path planning. Throughout all protocol, obstacle avoidance is emphasized, using potential field to determine the best angle of approach through summation of resultant attraction and repulsion forces. Using this method, based on its current conditions, the robot is able to avoid obstacles at all stages of the game.